Okay, now this is going to be a little application I just want to show you really fast, just to give you another sense that, in fact, you can use these simultaneous systems of many variables to solve things. And here's the basic question. Now, the basic question is going to sound a little bit weird. Suppose I give you this rational function. So let's just drop back to rational functions for a sec. That's just a polynomial divided by a polynomial. And suppose I say to you, hey, you know what? That actually is the answer to a question. And the question was, I had two fractions. One fraction had some mystery thing on top, but 3x plus 5 on the bottom, and some other mystery thing on this top, and x minus 2. And then I added them together, and I got that as the answer. Now, of course, I had to get a common denominator, and so the common denominator was the product of these things. But suppose I wanted to know what the fractions were individually before I added. So that is to say, suppose I'm given this rational function, and I want to split it apart into two pieces, this piece plus that piece. What's the right tops to make this thing actually work out? So I want to, instead of taking two fractions and adding them like I used to do, I now want to take this and break it apart into the sum of two fractions. This actually is called the technique of partial fractions, and believe it or not, people in calculus actually use this stuff. But let's not worry about why it's useful. Let's just see how we could do it and how it actually leads to a problem about two equations and two unknowns. And the trick is this. Since we don't know what the tops are, let's just give them names. I'll call this A and I'll call this B. So in fact, that will equal A, some unknown thing, over 3x plus 5, plus, and then B, some unknown thing over x minus 2. Now to figure out what A and B should be, let's just add these up. I have to get a common bottom. So here I multiply top and bottom by x minus 2, x minus 2. Here I multiply top and bottom by 3x plus 5, 3x plus 5. And now I add. The bottoms are the same. So in fact, this equals. Now let's see, what does it equal? Well, if I distribute here, I'd see an ax minus 2a, that's this thing, plus, and here I'd see a 3bx plus 5b, I distributed, all over the common bottom. I'm not going to multiply that out. I'm just going to write it out like this. And actually, I can combine these x terms here, and what I'd see is a plus 3b all times x, and the constant terms are, let's see, 5b minus 2a, all over the bottom. 3x plus 5 times x minus 2. Okay, so that's what we get when we take these two fractions and add them. Whoops. But I know what the answer should be. It should be x minus 5. And this is what I have. So that means is that the thing multiplying the x, that value right there, must be a 1, because that's what's multiplying this. So a plus 3b should equal 1. And this thing here, the number part, 5b minus 2a, well, that should equal this number part, which is minus 5. So in fact, to have this thing equal the actual answer, I need to have these match up. So the thing in front of the x needs to be the same thing. The thing that's a constant needs to be the same thing. So that gives me two equations and two unknowns. And so in fact, what I see here is the following. I see that a plus 3b equals 1. And I also see that minus 2a plus 5b equals minus 5. See, those two equations came from the fact that 1 has to equal the term in front of the x, and this has to equal the term here, because I'm equating this with this fraction, and then I add it up and saw how it came out. So in fact, I now have two equations and two unknowns. So now I solve this using a substitution method or any other method that you want. Let's take this and solve it for a. So a equals 1 minus 3b. If I now insert that here for a, what I would see is minus 2 times 1 minus 3b, that's just a, plus 5b equals minus 5. So if I distribute, I see minus 2 plus 6b plus 5b equals minus 5. And so 6b plus 5b, that's like about 11b. If I take that negative 2 and bring it over here, it pops over as a positive 2, but I've got a minus 5, so that's a minus 3. And so I see that b equals minus 3/11. What would a be? Well, I can go back to here and solve for a. A would equal 1 minus 3 times this. Well, a minus times a minus becomes a plus. 3 times 3 is 9 elevenths. 1 is 11 elevenths plus 9 elevenths. Looks like 20 elevenths. So a equals 20 elevenths. So what's the answer to the original question? The answer to the original question is A has to be 20 elevenths and B has to be minus 3 elevenths. And so, disappear. If I bring this back here, what I see is if I put in 20 over 11 as the number on top here and minus 3 over 11 as the number on top here, when you take those two fractions and combine them, what you get is that answer. So I just took this one fraction and split it into two fractions. The top here is 20 elevenths. The top here is minus 3 elevenths. But if you combine, getting a common denominator and adding, you'll end up with exactly this. This is the technique of partial fractions. And this is actually really important when you study calculus. Not that anyone will remember. But anyway, it's a nice application of taking a fact and setting up two equations and two unknowns. That's all.